All right, so let's get started again. I got some good questions in the break, actually. I just want to clarify a few things again. Let's take a step back. We're in the middle of this big, messy competition. So what is a bit uncommon here is the x0 and the training set, right? So I want to emphasize again that like the x0 is completely fixed. That point is not a training point. So the x0 is a separate point, which we fix all the way from the beginning. We fix it, and now we build a separate training set. So the x0 is never under any randomness or anything. It's just there. So that's, let's say, that's the cat picture that you want to get the true prediction on. That's how you measure if you do well or not. Can be anything, but it's fixed. Now we take training sets, which are different sets, and we don't only take one training set, but we pick many. So each training set we pick gives us one model when we train it. So that gives us one of these red dots. The training can be anything you like. We have no assumption on this. We don't say that the training is good or bad. It's just going to output a function. It's going to be complex or not. That's what you have chosen. If you train a complex model or simple one, it's going to just output this green model. So that's important to distinguish x0 from, has nothing to do with the training set. They're different. Another thing I should clarify is a bit this noise. So that's a bit funny that, why is this epsilon added here? So actually the thing is, this is actually just to make your life even harder. So what we say here is that if things would be nice, then we would actually see f of x in our training data, right? So remember, f of x is the true answer. It's the perfect label which generates a true label. So there would be. The thing is, we don't even see that. We see a noisy version of it. So the y's that we see in training, they are not the f of x, unfortunately, but they are noisy versions of that. And so also that's also true for your training. The training only sees the noisy version. So what's interesting is that even in that noisy labels which you have here, even then we can argue about what we're doing at the moment actually. So how much wrong are we going to be, no matter what model you use, how far off are we going to be to our fixed specified data point x0, which is not a training point. So again, so that clarifies what the randomness is, and now we see that we expect expectation over the noise, and we do expectation over these many training sets that you could get. Very important that they are of the same size. I only care about training sets of this fixed size for a moment to see, how different are these models that I can train on this. That's what we are doing, and we quantify this by the distance to these y's. Or actually, so we're going to see that we can get rid of the noise. So that's why we can even say something about the distance to the true f. The true f would be even better, right? That's what we would like to have, but we don't see it. We only see f plus noise. But let's see what we got. So I didn't explain everything yet. So we have this quantity here. Again, same thing that we tried to do. So we said the noise variance comes up, and then there are two other terms. And the first one is the bias that I tried to explain before the break. The bias is if you do this training infinitely many times for many different training sets, what's the expected f you get? And that is this expectation here. So, but let's see, I haven't defined yet what this S prime is. So what we're actually going to do is we're going to add an additional term in the middle to actually arrive at this sum here. But whatever, so for now, don't worry too much about S prime. This is just, again, any training set the same size. I will care about the expectation of this F. So if I train my F on S prime. I don't expect you yet to see why this is the equality that we're going to do in a second. But I first just want to convince you that does this make sense? Why is this a bias, right? So, and it's pretty clear. It's exactly our loss function. That's what we said. We want to measure using loss function. And then this guy. This is the truth, right? This is what would be the true label. Unfortunately, we only see a noisy version of it. But actually, this term describes how far we are away from that true value, the red value. If you do many, many trainings, then how far are you away from this? This is the bias, and it's very important that you remember this quantity. That's the definition of the bias term. Maybe before we actually see okay, no, let's define the other one. The other is the variance. So, and variance, again, we can go to the red part we had above here. So we have a random variable. We'll ask how far is it away from its expectation typically. So what variance are we talking about on the bottom here? So again, we have that it's a square. That looks good. The variance is always a squared value. And what this is measuring here is one training. So f of s train of x0. No expectation here. So that's actually a random thing, right? If you take many s, many, depending which training set you got, you will get a different value here. You remember these guys actually. These were the red dots in our image. So that's f of s train, which has been trained on my training set S. Good, and the other guy, it's a bit of an ugly formula, but this thing is exactly the expectation of the same quantity. So that's why this is a variance. This is the variance of one training compared to the expected training. If you train like 1,000,000 times or infinitely many times. So why did we do this? Some of this was S, some was S prime. That's super weird. But this we actually have to do to be clear that there are two expectations here. So I'm talking about a particular S train. That's what we actually had when we started here, right? That's this S train. So that is given. And now I want to talk about many expected trainings. That's why I introduced the S prime. And now we're actually ready to do a computation. So how do I get from here? How do I get to these two crazy terms? That's what we have to do, and then we are done. So this thing. Why is it the same thing as this? So that's what you have to prove in equation C. And this slide gets a little bit ugly, but I can write it here. So I'm going to keep these two terms. Maybe let's call this one A and this one B. And I'm going to add and subtract some simple quantity. So let's see what we get here. I'm getting an expectation. S train, I just write S, actually it's easier. Of A, and now I subtract and add some term. And then I have plus B, actually minus B. So I just want to add and subtract the same term in the middle now. And that's how the S prime comes into play. So far, we're on the same page. So A is this. That would be actually the truth we want to predict. B is what our simple model gives on this same X. And what we want to add and subtract here now is the expected thing when you do many, many trainings. And that's the S prime, because the name S is already used. That's why I introduce the S prime. Let's do this. I introduce the expectation of S prime of what? Well, the usual thing, just a prediction over many trainings. And now I train on S prime. So this is expected training on S prime. And I subtract the same thing. Okay, nothing happens. Just add and subtract the same thing. And yeah, I think you would agree that this is kind of an interesting quantity. So that's why, if it's an interesting quantity, we can think of adding and subtracting it. Let me color these guys red. Why do I color them red? Because if I do many, many trainings, then that's exactly the mean of all the red points. So that would be the dot here, right? That's my quantity I introduce now. So if I train my model many, many times in expectations, that's what it's going to answer from my y prime. Yes. I add and subtract this quantity. And what I care about is actually this quantity here, right? So that's now you can see it very clearly what we're doing, right? So there are many red points, okay, but I want to express the average distance of these red points kind of as I go from the red point to the center of the red points and then to the origin. That's kind of what we're doing intuitively to understand this quantity better. So that's this quantity here. We add and subtract. Here it is, expectation over many trainings. And I just given them a different name because in this whole expression, the training set S train is already specified. So I add and subtract these guys. So yeah, let's maybe do the computation. There is actually a mistake. The red formula is wrong. What did I forget? Does anybody see that? So I forgot a square. That's correct. So it's a minus b squared, because here there is a square. So that's what we want to do. Now, any ideas what to do? We do our favorite trick. U plus v squared is u squared minus v squared. Well, plus actually, and then there's the mixed term. Let's first do the u squared and v squared. And yeah, there's nothing to do actually. We're already done the a minus this. So my u is exactly my bias. U square is the bias. V square is the variance. Okay, for u square, why is this? Well, it's exactly the same thing as we have written. Yeah? F of x minus this thing, which is the expectation over many trainings. That's the bias, as we said. Why is this the variance? Let's check. We have the same expectation minus b. B is one model trained on and evaluated on x0. So this here you can see this is b. And then this quantity here, that's again, that is exactly the red quantity, so that's what you want to have. Okay, do you agree with me that this is bias plus variance, except that we forgot the mixed term? So what about this thing, 2u times v? That we have to check a bit more. But otherwise, I hope you agree with me on this. Okay, almost done, because it will be nice actually, because the mixed term is 0, so it's not too bad. So what we get as an end result is that the bias is a systematic error. Our model is wrong, like all the red points, they're wrong on average. So, and then actually I could also color this one. Then now I have my new color, I can color this red as well. That's much more convenient because they are the same. And this is the center of all your shootings. So the center of all your shootings is systematically off from the truth. That's the bias. And then also, these models you actually train, they're how far they are away from their red center. So that's exactly, how far they're away from the red center, and then how far is the red center from the truth. That's the idea here. And the sum of these things squared, magically, it's exactly this quantity of our interest. So they do compose this nicely. If this mixed term is 0. Any questions?
I have 2 questions. So we need 2 training sets to compute the expectancy of the training set?
We have 2 training sets here. We actually have much more. We have so this is not something you would do. This is not something you could ever do in practice. This is only a theoretical experiment. We can never, because the expectation over all training sets of this size, that's impossible for us to do, because the data is infinite. So we cannot do infinitely many trainings, right?
Can we do an estimation of it?
You could do an estimation of it, yes. Yes, you could do this. That's actually a bit what cross-validation does, right? There we try like 4 different training sets. The difference is what there we tried it on 4 different test sets. Here we actually measure everybody on the same x0. So here it's a bit simpler. We measure on the same x0, but you're right. The different training sets is a bit like cross-validation. If you wanna do this practically, then that's what you would do.
Yep. How is the mixed term 0?
How is the mixed term 0? Yeah, that's what I have to do now. That's not completely trivial, but it's also not super hard. So the mixed term is u times v. So that's, we will look at it, and actually it's here. So yeah, maybe you need a quiet minute at home, but so here is the mixed term u times v. Looks a bit nasty, and it actually is. Also there should actually be a 2 in front of it, but it doesn't matter. So why are there 0? So you just have to multiply this out. These are 2 things times 2 things. So if you are careful, what depends on what? So the stuff here does not depend on s at all. So there are 2 s's now. One is the s, one is the s prime. But the stuff in the circle here does not depend on s. So the expectation disappears. From the v, we have not changed anything, except now we have taken expectation over s and of s prime, because that's the expectation here. Yeah, sorry, this looks nasty, but remember these are the centers of the red points. Just think that this is, give it a different name, then it's much easier to think about it. So these guys, yeah. So we have two expectations now over S and S prime. Nothing has happened. I just observed that the V will actually depend on both of them, while the U doesn't. U is only defined on S prime. That's the first equality here, very simple. Second one, what's happening here? So nothing changed on the left. And on the right, I've now looked a bit at this. I looked at, oh, this one does not depend on S at all. It only depends on S prime. Actually, it's unchanged. It's what it always was. That's our favorite center of the red points. So the only thing we have to care about is these two things. So what is expectation over S of f of S? And now that's interesting. That's this guy here. It turns out this is the exact same thing, but just with a different name. So that's why they're actually 0. So this is why the whole thing is 0, which is very good. There's no mixed term. So that's, yeah, it looks a bit funny. So maybe don't worry too much about it, but do this computation in a minute at home. And the intuition about this is that you kind of have this Pythagoras thing. So they are actually orthogonal, right? So the situation is not as bad as I showed. It is 2 errors, but the reality is actually, I have to redraw the stuff. So this is the variance. How far are the red points away from the center, from their center? And then the bias is how far is this center away from the truth. So the blue arrow is the bias. And what we have, the trick we did is actually we saw they have no mixed terms, so they are kind of orthogonal. So that's why there was no mixed term, if you want to think about it this way. So if you like geometry, that's one way to think about it. If you don't trust geometry, do the computation. It's always good to do the computation. It's not obvious why they should be orthogonal. So the mixed term is 0. So then let's see again what we got. Nothing special, but we have now these 3 terms: noise, the bias, and the variance. Noise is kind of unavoidable because that has been put between us and the true nature. So we only observe everything under noise. There's no way you can avoid it, let's say. So it intuitively makes sense to have noise appearing as an additive term, kind of, and that's also what we got here finally. So we have these 3 terms. Okay, let's try to interpret this a bit more, and that's the last thing we want to do here. So we have these 3 terms, and they're all non-negative. Let's check. They're all squares, so that's why they're non-negative, or expectations of squares. All right, so they are actually, we cannot compute all of these 3, but maybe some of them you can get a bound on. Or let's say if somebody tells you what is the noise, how is this going to help you? Well, it's not really helping you, but it's telling you that no matter what you do, there is no way you can get better than this noise, because the noise is one of these 3 terms, and the others can only make it larger. So this is a lower bound on the error we can get. Error, same thing we always talk about. That's the true f minus what your model predicts. So that's the noise. The bias term is we also defined this many times, the difference of this red center minus what it should be. And so yeah, that's the main quantity if you're systematically wrong. And then the variance is how far you're off on average from that red point. So there is a different interpretation of bias. So this is kind of a joke that, well, motivation or sarcastic motivation that, yeah, only consistent is not good if you're systematically wrong, right? So here it's just, you have zero variance here. The arrow is always perfect, right? All the points go in here, zero variance, but the bias is big. So here is the bias, then, and variance is zero. So that's the same thing that we talked about. This, it's not interesting from a variance point of view, but it's interesting to explain the bias point of view. So, okay, we have three terms. We said they're all non-zero, and yeah, can you estimate them? That's not so easy. But what you can do is to do like a few trainings. Of course, not infinitely many, but like maybe 10 trainings, as you do in 10-fold cross validations. And look a bit, yeah, how different is how much variance do your predictions get? So the only problem is in reality you cannot compare this to the truth. You don't know the truth, but you can still get an idea of this, and that's what we did. What we did last time when we looked at the test error or in the lab today, like in this plot here. So. So complicated. Now we need to relate this to models again. The simple models, they have often almost no variance, but a huge bias. So maybe I should go back here. Simple models is case 1. Systematically wrong, but always the same, no matter how many times you train it, how many different data you use. And the complicated models, they're case 2. Complicated models are, on average, they're perfect. They can predict anything. So they can predict what they shoot the center. But if you give it a different training set, it will be very different. A different model will appear. So they will have a lot of variance, and you're not going to get this robustness. That's what overfitting is, and that's also an interesting phenomenon. So we have seen both extremes, and now today we were able to quantify this a bit in the case of this model when we assume that the data comes from this unknown f of x. Okay. So yeah, that's almost it. I have a few examples which I want to have a look here, and so here's when we would do a real regression and one variable, and you would look at different complexities. So how do we actually see this bias and variance in practice? So here we do regression, one variable. The black curve here, that would be the f of x. So now it becomes a bit more concrete. Maybe I should have done this at the beginning. So this would be the truth. You're trying to fit it. One attempt to fit it is with a linear model. The yellow one here. That's the simplest one. And then we have there is a small, blue one here, which is maybe polynomial of degree 3 or something. And then we have the green one. So that's this guy. So that model seems to be overfitting a bit. And that's the 3 points we have here. So on the plot on the right, I plotted the same thing as you did. So red is always a test error. Test error of the green model is pretty bad. But the training error of the green model is super good. So it's a perfect fit. So that would be an overfitting model, because so here is a complex model. The other extreme is so blue is kind of the middle, but the yellow model is the worst one. I maybe shouldn't write in yellow. So that's the simple model. So the linear model. So too simple, and that's why it gets a very bad training error, and actually also a bad test error. So both is bad here. And the sweet spot is in the middle. So in the middle we have a model of the right complexity, not too complex, not too simple. And that's the blue point here. You can see the polynomial of degree 3 or whatever. That was maybe the best fit for this scenario. So again, this is if you have this size of data. So we don't have infinite data, right? We have to work with a finite data set. And if you work with the same size but take a different data set, you will get a different training. The green curve will look completely different if you take a different data set of the same size. The blue and the yellow curve, they will not look so much different. So that's why they have much less variance. Okay, I hope this makes sense. Then I have the same thing again, but now we have a different 2f, which is actually simpler, but the story is exactly the same. And the same thing we have here again, so you can look at this is a bit to explain which models give you a good fit, which ones give you a bad fit. Same story there. This is just to illustrate that some models, so the one we had at the beginning was kind of okay. On both sides it got bad. In the test error went up on both sides because one has high variance, one has high bias. This is the same thing, but it just looks a bit different. So this one here gets very high variance here, so the test error gets very bad. And the other one here, if you want to think about it, that gets very bad when you fit a simple model. So, but when you fit a complex model, it's actually not so bad. So it can vary a bit. And yeah, that's the whole bias-variance decomposition story. So maybe think about this again if you look at your lab on the plots you got. They look basically the same as we had here. Yeah, any questions on this? So this was a lot of theory, except maybe this practical one gives you a good intuition. Any questions about the theory or the practical lab on this? So I tortured you a bit with computations today, yeah? The bias, yeah, we don't have different test set, but the bias is only about, here it's only defined at one particular x0, so it will change if you take a different test point. So yeah, but it's an expectation over all the training sets. If you look at it, yeah, here's the bias. So about all possible training sets you could get that size. So that's all these red shootings. So it talks about all of them, but it only talks about one point where we evaluate it. So yeah, it's not exactly the same as we did with the test error, but you can think of it as the exact same thing happening. If you have a test set as we did in cross-validation, then you will just have more than one test point, but the exactly same thing will happen. So S prime and S have actually the same meaning. So they're just different names for it because we need to do it separately for two terms. So this is completely the same expectation. So I take all possible trainings I can get, and then it's just because I want to talk about this red center, and then I want to talk about the variance. So the variance has two expectations, right? If you look at the definition. And I just want to make very clear which one we're talking about. That's the only reason why we were talking about S and S prime. So it's just a name. It's nothing different here. Yeah. Other question, yeah? Yeah, that's a very good question. You ask, yeah, if you would know that your true model is degree 3, should you always make that your class of models over you train on? Yeah, I would say basically yes, but it depends how much noise you have. So that's not, if there would be no noise, yes. But because there is noise, you might actually overfit to the noise. So it's, you have to be careful to play with that. But yeah, I would say try it out, and you will actually see when you do cross-validation. So this is a bit of the theory story, and the practical story for the same thing is cross-validation, because that you can really do and experience how good and bad it does. So, but this is the theoretical philosophy behind it. Yeah. All right, then I would say we wrap up. And so next week is a little bit different from a regular week. Actually, now we're going to switch for a bit. That Rüdiger Robanke will teach for a few weeks, and I will come back for natural language processing. But now we've done so much theory, this was a bit demanding. So next week we want to be very practical. We want to show you, yeah, two real things, and one is real applications, machine learning for real use cases in industry and practice. We have speakers from Google Brain, and the other one will be from, yeah, I'll actually let Emmerich explain this, because he will take this over next week.
Okay, thanks. So, hello everybody. So my name is Emmerich Delvaux. I'm a research scientist in Martin's lab. And so, as I said, next week the program will be different. We'll have 2 research talks, and I will be organizing and hosting those talks. So, if you have any questions regarding organization or the talks, you can talk to me next week. I will be there during those sessions. And these research talks are great opportunities to discover, as he said, different insights on machine learning and applications. On Tuesday, we'll have 2 outstanding researchers from Google Brain talking about transfer learning and AutoML. So transfer learning is the task of transferring some knowledge that you have gained while solving a task on a different task, which is somehow related. So as one would expect, there is some knowledge that will be observed. And AutoML is the task of automating the machine learning pipeline in order to make it simpler for the practitioner. And on Thursday, we have Emmanuel Abbé, who is a new professor at EPFL, coming from Princeton before, who will talk about stochastic block models and community detection. So it's a task which importance could hardly be underestimated, because stochastic block models are used both on the theoretical side and in applications to model social networks, which of course have become one of the most important tasks in machine learning. So we are very happy to have these talks next week, and if you have any questions, you can ask me or Martin.
Okay, thanks, and have a nice evening.